The Andromeda Galaxy has been instrumental in transforming our comprehension of the universe, our place within it, and our own galaxy. The Milky Way is just one of the billions of galaxies that populate the observable universe. Learning about Andromeda, the galaxy closest to us, has provided crucial insights. With the advent of advanced observational tools, such as the James Webb Space Telescope, JWST, our perspective on Andromeda has undergone significant changes. Recent data from JWST has not only confirmed our previous understanding, but also introduced new puzzles that scientists are working to address. The telescope's findings have even resulted in surprising signals from Andromeda, which have left the scientific community intrigued. Throughout history, our perception of the Milky Way has evolved dramatically. In earlier times, when our technological capabilities were rudimentary, the Milky Way appeared as a hazy band of light across the night sky. This observation led to various interpretations and myths, with the Milky Way often being considered a mystical and central element in many cosmological beliefs. However, with the development of telescopes and the work of astronomers like Galileo Galilei, we began to understand that the Milky Way was not a celestial concept but a vast collection of stars and other cosmic entities. Galileo's observations in the early 17th century challenged the prevailing Aristotelian view, demonstrating that the Milky Way was composed of numerous individual stars rather than a single light source. A significant leap in our understanding of galaxies came in 1920 when American astronomer Edwin Hubble used the Hooker telescope at the Mount Wilson Observatory to observe distant nebulae beyond the Milky Way. These observations revealed that these nebulae were not part of our galaxy but were separate galaxies containing billions of stars. Among these discoveries was the Andromeda Galaxy, also known as M31, which has a rich history of observations dating back to the 10th century, when the Persian astronomer Abdul al-Sufi described it as a small cloud in his star charts. Despite its faint cloud-like appearance, Andromeda was visible to the naked eye, a feature that continues to make it accessible to astronomers today. It wasn't until 1620 that a more detailed description of Andromeda was provided by Simon Marius, who used a telescope to observe the galaxy. His work laid the groundwork for future studies of celestial objects. In 1864, English astronomer William Huggins made a groundbreaking observation by studying the spectrum of light from Andromeda, which differed from that of typical nebulae, confirming that Andromeda was indeed a separate galaxy. This finding was crucial in establishing Andromeda as a distinct galaxy and provided valuable insights into its nature. The Andromeda Galaxy is a colossal structure with a mass estimated to be between 1 and 2 trillion times that of our Sun. Despite its relative proximity in cosmic terms, Andromeda's immense size and mass make it a significant object of study. It is believed that Andromeda's formation involved the merging of several smaller galaxies through a process known as galactic cannibalism. This process, where smaller galaxies are absorbed into a larger one, contributes to the galaxy's growth and complexity. Recent research and advanced observational techniques have led to a re-evaluation of Andromeda's structure and mass. New findings suggest that the masses of the Milky Way and Andromeda are much closer than previously thought. One of the most intriguing aspects of the Andromeda Galaxy is its supermassive black hole, which exerts a powerful gravitational pull on the surrounding stars. These stars' concentration and speed vary depending on their proximity to the black hole. The black hole's gravitational forces cause the stars to move at high speeds, contributing to the bright central region observed in Andromeda's active galactic nucleus. Another fascinating aspect of the Andromeda Galaxy is its abundance of globular clusters. These are tight groups of stars that orbit around the galaxy's center, similar to satellites. Andromeda is estimated to harbor around 460 of these ancient clusters, each containing hundreds of thousands to millions of stars. The presence of so many globular clusters provides valuable insights into Andromeda's history and its interactions with smaller galaxies. Recent observations suggest that Andromeda may be undergoing a transformation, transitioning from a typical spiral galaxy to a ring galaxy. Ring galaxies are characterized by their circular or elliptical ring-like structures with bright stars in the rings and relatively little luminous matter in the central region. There are 3 main types of ring galaxies: nuclear rings, inner rings, and outer rings. Ring galaxies are considered rare, and their formation is often triggered by collisions between galaxies, or when a smaller galaxy passes through the center of a larger galaxy, forming a ring-like structure. One of the most thrilling prospects in contemporary astronomy is the anticipated collision between the Milky Way and the Andromeda Galaxy. This colossal event, referred to as the Andromeda-Milky Way collision, is predicted to occur in about 4 billion years. While this timescale is vast in human terms, it is relatively short on the cosmic clock. The collision will initiate a complex and prolonged process of galactic merging that is expected to span an additional 2 billion years before the two galaxies fully coalesce into a single new galaxy. As the Milky Way and Andromeda galaxies approach each other, their gravitational interactions will become increasingly significant. The initial phase of this encounter will involve a gradual but dramatic restructuring of both galaxies. The collision will not be a sudden impact, but rather a series of close encounters that will bring the galaxies progressively closer. This will result in intense gravitational interactions that will distort their shapes and compress their stars. The interaction between the galaxies will trigger the birth of new stars in vast stellar nurseries, creating spectacular cosmic structures. While the intense star formation will light up the night sky with brilliant new stars and star clusters, it will also lead to significant changes in the structure of both galaxies. The merging process will gradually reshape the galaxies, eventually resulting in the formation of a new, larger galaxy, often referred to as a supergalaxy. This new galaxy is anticipated to be an elliptical galaxy characterized by a smooth, rounded shape and a more uniform distribution of stars, contrasting with the spiral structures of the Milky Way and Andromeda. Despite the dramatic changes expected, it is unlikely that our solar system will be ejected from the galaxy or suffer significant changes in its orbital path. However, the altered galactic environment could lead to changes in the night sky's appearance from Earth, with new stellar formations and rearranged constellations offering a dramatically different view of the universe. The merging of the Milky Way and Andromeda promises to be a cosmic event of immense scale and beauty, reshaping the galaxies and transforming the cosmic landscape. The merging of the Milky Way and Andromeda could also lead to increased cosmic radiation, affecting Earth's atmosphere and ozone layer. These changes might influence climate and impact the survival of various species. Although the direct effects of galactic mergers are generally distant and gradual, their potential impact on planetary systems and life cannot be entirely ruled out. Understanding these processes is crucial for comprehending the broader implications of cosmic events on the habitability and stability of planetary systems within our galaxy. In conclusion, the merging of the Milky Way and Andromeda will be a slow and gradual process spanning billions of years. The dramatic changes anticipated will offer valuable insights into the future of our galaxy and the broader universe. As our observational tools and techniques continue to improve, we will gain a deeper understanding of Andromeda and its role in shaping the cosmos. The story of Andromeda reflects the dynamic and ever-evolving nature of the universe, offering a glimpse into the future of our galaxy and the broader cosmic environment. Unveiling Andromeda's cosmic environment. The Andromeda Galaxy, known scientifically as M31, holds a plethora of intriguing cosmic phenomena that extend our understanding of galactic structures and processes. Beyond its well-documented features, Andromeda offers a window into the dynamics of galaxy formation, evolution, and interaction. The role of dark matter in Andromeda. Dark matter, an invisible and enigmatic substance that does not emit, absorb, or reflect light, plays a crucial role in the formation and behavior of galaxies. In Andromeda, dark matter is thought to constitute the majority of the galaxy's mass, influencing its structure and rotation. Observations suggest that the distribution of dark matter in Andromeda is similar to that in the Milky Way, with a dense, spherical halo surrounding the visible components of the galaxy. This dark matter halo is integral to understanding the galaxy's gravitational binding and its resistance to being pulled apart by interactions with other galaxies. Research on dark matter in Andromeda involves studying the galaxy's rotation curve, which is the plot of the orbital velocities of stars and gas clouds against their distances from the galaxy's center. The rotation curve of Andromeda reveals that its outer regions move at speeds that cannot be accounted for by visible matter alone. This discrepancy indicates the presence of a significant amount of dark matter exerting gravitational influence on the galaxy. By analyzing these curves, astronomers can infer the density and distribution of dark matter in Andromeda, contributing to our broader understanding of its role in galaxy formation and evolution. Stellar populations and chemical enrichment. Andromeda's stellar populations provide valuable insights into the galaxy's history and evolutionary processes. The galaxy hosts a range of star types, from ancient population 2 stars found in its globular clusters and halo to younger population 1 stars located in its disk and spiral arms. The chemical composition of these stars, particularly their metallicity, offers clues about the galaxy's formation and the chemical enrichment over time. The study of star clusters, both globular and open, reveals the processes of stellar nucleosynthesis and the chemical evolution of Andromeda. Globular clusters, which are some of the oldest components of the galaxy, contain metal-poor stars that formed early in Andromeda's history. The metallicity of these stars provides evidence of the initial conditions of the galaxy and the rate at which it has accumulated heavier elements over billions of years. In contrast, younger open clusters and field stars exhibit higher metallicities, reflecting more recent stellar nucleosynthesis and the ongoing enrichment of the interstellar medium through supernovae and stellar winds. Andromeda's satellite galaxies and tidal interactions. Andromeda is surrounded by a collection of smaller satellite galaxies, which play a significant role in its overall structure and evolution. These satellite galaxies, including the M32 and M110, interact gravitationally with Andromeda, influencing its morphology and star formation processes. The tidal forces exerted by Andromeda on its satellites result in observable phenomena such as tidal tails and streams of stars. Tidal interactions between Andromeda and its satellites can lead to complex dynamical effects, including the stripping of stars and gas from the satellites and the formation of new stellar populations in the tidal streams. These interactions provide valuable information about the history of Andromeda's accretion of smaller galaxies and the impact of these processes on its current structure. For instance, the discovery of extended tidal streams around Andromeda suggests a history of multiple mergers and accretion events, which have contributed to the galaxy's growth and the formation of its halo. The Andromeda Galaxy's interstellar medium. The interstellar medium, ISM, of Andromeda, consisting of gas and dust between the stars, plays a vital role in the galaxy's star formation and evolution. The ISM is composed of various phases, including ionized, atomic, and molecular gases, each with distinct physical properties and contributions to the galaxy's dynamics. Observations of the ISM in Andromeda provide insights into the processes of star formation, the distribution of interstellar matter, and the overall health of the galaxy's ecosystem. Molecular clouds in Andromeda are regions of dense, cold gas where new stars are born. These clouds are sites of intense star-forming activity, and their study helps astronomers understand the life cycle of stellar populations and the processes that trigger star formation. The interaction between stellar feedback, such as supernova explosions and stellar winds, and the ISM regulates the formation of new stars and the evolution of the interstellar medium. Observations of these interactions in Andromeda offer a comparative perspective with the Milky Way and other galaxies, enhancing our knowledge of galactic ecosystems. Insights from Andromeda's galaxy clusters. Galaxy clusters, which are large groups of galaxies bound together by gravity, provide a broader context for studying individual galaxies like Andromeda. The Andromeda Galaxy is part of the Local Group, a collection of more than 50 galaxies, including the Milky Way, the Triangulum Galaxy, and numerous dwarf galaxies. The dynamics and interactions within the Local Group influence Andromeda's evolution and offer clues about the larger-scale structure of the universe. Galaxy clusters, such as the Virgo cluster, in which the Local Group is a member, contribute to our understanding of the distribution of dark matter and the large-scale structure of the universe. Observations of galaxy clusters help astronomers understand the processes of galaxy formation and evolution on a cosmic scale. By studying the interactions between galaxies within clusters and their influence on surrounding structures, researchers can gain insights into the hierarchical growth of galaxies and the role of environmental factors in shaping their properties. Andromeda and the cosmic microwave background. The cosmic microwave background, CMB, radiation, a remnant of the Big Bang, provides a snapshot of the early universe and serves as a crucial tool for understanding cosmic evolution. Observations of the CMB have revealed important information about the initial conditions of the universe and the formation of cosmic structures. The study of Andromeda and its interactions with other galaxies can be placed within the context of CMB observations to understand the evolution of large-scale structures and the influence of dark energy on cosmic expansion. Research on the CMB helps astronomers refine models of galaxy formation and evolution by providing constraints on the initial density fluctuations that led to the development of galaxy clusters and superclusters. By comparing the observed properties of Andromeda and other galaxies with predictions from cosmological models, scientists can test hypotheses about the role of dark matter, dark energy, and other fundamental components of the universe in shaping cosmic structures. Future observations and discoveries. As observational technology continues to advance, new discoveries about Andromeda and other galaxies will provide deeper insights into the universe's workings. Upcoming space missions such as the James Webb Space Telescope, JWST, and ground-based observatories with next-generation instruments will allow astronomers to study Andromeda in unprecedented detail. These observations will shed light on the galaxy's structure, composition, and interactions, furthering our understanding of cosmic phenomena. Future research will likely focus on unraveling the mysteries of dark matter and dark energy, understanding the processes of galaxy formation and evolution, and exploring the complex interactions between galaxies in clusters. By combining observations from different wavelengths and scales, scientists will continue to refine their models of the universe and its components, ultimately enhancing our knowledge of the cosmos. Implications for galactic evolution. The study of Andromeda and its interactions with the Milky Way and other galaxies has significant implications for our understanding of galactic evolution. The merging of galaxies, the role of dark matter, and the dynamics of stellar populations are all critical factors in shaping the structure and behavior of galaxies. By examining these processes in Andromeda, researchers can gain insights into the future of our own galaxy and the broader evolution of the universe. Understanding the outcomes of galactic mergers, such as the transformation of spiral galaxies into elliptical ones, provides valuable context for predicting the long-term evolution of the Milky Way and other galaxies. The study of Andromeda's interactions with its satellites and the larger cosmic environment helps astronomers build comprehensive models of galaxy formation and evolution, offering a glimpse into the dynamic and ever-changing nature of the universe.